Hi Year 10, so we're going to go through your written answers in this video. So this is section 2 of your end of year paper, and question 1 shows you a snowboarder moving down a ski slope, and you then get given a speed time graph. So you can see that because we've got speed on the y-axis and time on the x-axis, the gradient of your graph would be acceleration, which will be useful in a later part of the question. So the first thing is that it tells you the mass of the snowboarder is 75 kilograms, and it asks you to calculate the maximum kinetic energy of the snowboarder. Okay, so we know the kinetic energy equation is a half mv squared, and so we know that this number will be biggest when all of these numbers are as big as possible. So the mass is fixed, it's 75 kilograms, but the velocity, if you look at the graph, changes. Okay, so you have to find when the speed is as big as possible. Okay, you can see I've highlighted that at 5 meters per second. And so that is the value that you're going to put in, because that's when it has maximum. Okay, and then when you sub that into the equation, you get your 940 joules. To two significant figures, but don't worry if you left it as 937.5, that's fine. Then the next part of the equation asks you to then calculate the acceleration of the snowboarder in the first 10 seconds. Okay, so this is the first 10 seconds here. So you can see that during that time, the graph is a straight line graph. Okay, so it's got a constant gradient, so it has a constant acceleration. And what we are going to do is calculate that gradient. So we're doing change in y divided by change in x. Okay, that's the gradient. So we've got 4 take 0 as the change in y, and we've got 10 seconds as the change in x, which is why we've done this sum here. Okay, because this is acceleration, final velocity minus initial velocity divided by time. Okay, now lots of you nearly got 3 marks, but you forgot to add the little squared and you were writing metre per second. Okay, so don't forget that acceleration is metres per second squared. Okay, so question 2 in this section then is about an astronaut driving on the moon, and it tells you that the vehicle and the astronaut have a total mass of 300 grams. Okay, let's see, make it a little bit clearer. And then it says, on the moon, the gravitational field strength is 1.6 newtons per kilogram. Gravitational field strength is g, okay, it's acceleration due to gravity, it's the same thing. So when we calculate the total weight of the vehicle and the astronaut on the moon, weight is still mass multiplied by gravity, but this time the gravity value is not 10 like it is on Earth, it's much smaller, okay? And that's why we get 480 newtons, 300 multiplied by 1.6. That's why you can bounce around on the moon, you feel very light, because your weight is a lot less. Then it asks you to calculate the acceleration if the vehicle has a force applied to it of 600 newtons. So we know that force is equal to mass multiplied by acceleration, and I can rearrange that equation, and I get acceleration is force divided by mass. I'm told in the question that the force applied is 600 newtons, okay, and the mass is still 300 kilograms, that never changes. So 600 divided by 300 is 2, so the acceleration value is 2. And again, it's meters per second squared. Okay, let's have a look at question number 3 then. So this bit was done pretty well actually. So it says that we've got a car travelling at 5 meters per second. You can see that's to the right. But it's passing another car that is also travelling at 5 meters per second. And the direction is shown by the arrow, so you need to look in the diagram. And it says, explain why the cars have the same speeds but not the same velocities. Okay, so remember that speed is a scalar, okay, so it only has a magnitude, whereas a velocity is a vector. Okay, so not only does it have a magnitude, it has a direction as well. So you can see they're moving with the same magnitude, so the same size of their speed, but they are moving in opposite directions, so they don't have the same velocity. Okay, then in the next bit of the question, it tells you how far the car travels. It says it travels 2,000 metres, and it does that for 120 seconds. And the force during that time from the engine is 12,000 newtons. And it asks you to calculate the work done. Okay, so the first thing is it asks you to name the equation. So work done is force multiplied by distance. The force is the 12,000 newtons. And the distance is the 2,000 metres. Okay, and that tells us that we get 24 million joules of energy transferred during that time. Okay, so this is the number that you should have got in joules. This is an energy. Now in the next bit of the question we had a little bit of trouble, and I think that is because you saw the word useful and thought that that meant efficiency, and it doesn't. It's not asking for the efficiency, it's asking for the power output. Okay, so power is energy divided by time. Okay, and the useful energy was the energy that made it move. So it's this value here. So we take that energy value and use it. And we divide it by the time it took to transfer that energy. And we then get our 200,000 watts. Okay, so let's have a little look at 24. So we've got a spring that has been hung from the top of a bench. And we can see that it is 29.8 centimetres long to begin with. And then we hang this load, okay, so we add a force onto the spring and it makes the spring, crikey, it's like a tongue twister. So originally it was at this level, but the load pulls it down to here. Okay, so this distance is the spring's extension, so we just need to find x. Okay, so we just find the difference between the 2 points and we get 33 centimetres for that one. That was pretty well done. Okay, then it asked you to find the numerical value of the spring constant. They even give you the equation. Okay, so the force F is equal to K the constant X extension. Okay, and you are asked to find the constant. So for help, I've put this into a triangle. These two things get multiplied together, constant, extension, to get the load. If I want the constant, I cover up the C and I can see L divided by E, the load divided by the extension. Okay, so I then take the load value, which is given up here, it's 5.5 newtons, and I divide it by the extension that I just calculated. And I'm going to get 0.166666 recurring, but I'm not going to write that down. I'm just going to give it to two significant figures, 0.17. Okay, now suggest a suitable unit for the constant. Remember, the constant is a load divided by an extension. So I need to find the unit of the load and divide it by the unit of extension. So load is a force in newtons, and I then divide that by the unit for extension, which is centimetres in this case. You could have got away with saying Newton per metre, that would be okay as well. Alright, this is question 5 of this section. So you've got walls that have been built by 2 bricklayers. Okay, and they are the same wall, so the weight of these is the same, but in A, it's sitting on top of a foundation that is very wide, okay, whereas in B, it's very narrow, okay, so the area that is spread over is much smaller. So we've got a large surface area, a small surface area. The question asks you, which is least likely to sink? Lots of you told me which ones are more likely to sink, and you weren't wrong, but it doesn't answer the question. Okay, so we have to have a little look and think which one is least likely to sink. hopefully just from your life experience you can see that A is more likely to stay where it is. So you get 1 mark for getting it right and then 1 mark for explaining. So we say the wall that puts less pressure, that's the word you want to use there, on the concrete is the least likely to sink. We know that pressure is force divided by area, but the force is the same for both of them because they're the same weight. But the area is much bigger for A, so we're spreading that force over a bigger area. So that one has the least pressure. Okay, so that one's least likely to sink. So pause if you need to add your answer before carrying on. Then you're given 2 squares, P and Q. And it says that the atmosphere is pressing down on P and Q, which it is because the atmosphere is just air. I've got air above this piece of paper right now, and there will be air colliding with these 2 squares. Okay, now in order to calculate the amount of pressure, I would need to know 2 things, the force and the area. But it's not enough to just write those 2 words. I have to give more detail. Okay, so what force? What surface area? So the force comes from the air hitting it. Okay, so every time an air particle hits P, it exerts a little force. So what I want to say is I need to know the force exerted, which just means put on, P, from the air, okay, by the air particles. And I need to know the surface area of P as well. Okay, so it's not enough to just say force and area. All right. The area of P is 4 times that of Q. Complete the following sentences. The atmospheric pressure on P is blank the atmospheric pressure on Q. Okay, now P and Q are physically next to each other. The air around P and Q is the same, it's pretty uniform, okay? And so in P, you'll have air particles kind of looking this close together, and you'll have the same in Q. They'll look as close together, but in total there will be less air particles hitting Q. Okay, so if there are less air particles hitting, there's less force. So even though the area has got smaller, so has the force, and it makes the pressure the same. Okay, pressure is force divided by area. Okay, so we know that at the same point in space, pressure from air is the same. Otherwise, your fingernail would feel a different pressure to your head because they're different sizes. Okay, but it doesn't. That's not what happens. You feel the same air pressure all over your body. So, pressure is the same for both. Okay, but the force on the on P, because of the atmosphere, is going to have to be 4 times bigger. Okay, so look, if P's area is 4 times that of Q, the force on 1/4 of P will be equal to the force on Q. Okay, so we've got force divided by area is the same here as it is here. Okay, but we've actually got 4 times that area. Okay, so we've got 4 times the area. We're going to need 4 times the force, so that when we divide the 2, I get the same pressure. That's the same as F over A for Q. The 4's cancel to make 1. Okay, so the only way to keep the pressure the same, because pressure is the force divided by the area, is if both things change by the same amount. Okay, so we're going to say it's 4 times bigger because the area is also 4 times bigger. Okay, 26 then, or section 2, question 6. We've got energy resources. You have 3 marks, so you're going to need 3 ticks, and it asks you to choose which are correct. So the first one is about building hydroelectric power stations, and it says they have an impact on the environment. Well, a hydroelectric power station needs a big reservoir of water up high that is then allowed to travel down through a turbine. Okay, but in order to build this in a country, this thing here is absolutely huge. Okay, and it often requires us to flood land. Okay, so that does have an impact on the environment, so that is true. Burning fossil fuels produces atmospheric pollution. Well, I really hope that you know that that's true. It's all over the news at the moment with the G7 climate change summit. So just please don't get this one wrong. We know that fossil fuels are bad and they are polluting. Wind turbines are turned using gravitational potential energy. No, they are not. If it's about turning, that's movement. Okay? And the energy of movement is kinetic energy. Okay, so wind turbines are turned using kinetic energy. Coal and crude oil are sources of renewable energy. Obviously not true, they're running out in our human lifetime span. We're going to run out of that. And then geothermal energy is obtained from hot rocks below the ground. If you are clever, you will use the next question to help you with that one. You could go back and tick it because you know it's true. Okay, number 7. You've got a list of energy sources here to produce electricity. It asks you which ones are non-renewable. Notice that it says sources plural, and it then even puts in bold each, which tells us we need more than one. Even though it's worth 1 mark, you have to circle both to get the mark. Okay, gas and oil are non-renewable there. Okay, so then we've got, in part B, a picture of the power station, and it asks you to describe how the power station generates, and this word's important, electricity, and it's worth 4 marks, so I'm going to need 4 points. Okay, so let's have a look. The first thing we can see from the diagram is the cold water is pumped down to the hot rocks. You can't just write that because that's already given to you, but what you need to say is that cold water is then heated by the rocks and turned to steam. That's the first thing that happens. So this cold water becomes steam. The steam is then pumped back up and it turns a turbine. So here what we actually have is a turbine, and you get a mark for knowing that steam turns a turbine. That's the word we're looking for. That turbine is connected to a generator. So that's the third bit. The turbine drives a generator. And then the fourth bit is for saying that you know that generators make electricity. Now lots of you wrote the word energy, okay, which is not right. It's asking how we make electricity, not just any energy. So make sure you've got all of these points, please. Pause if you need to and write your answer down. Okay, number 8. We've got a beaker. It has liquid inside of it. It's on a balance, so you can see that everything that's on the balance has a mass of 1,100 grams. And that's the beaker itself plus the liquid inside. And it tells us that the empty beaker is 400 grams. So the liquid must be the difference between those two. Okay, so the liquid must be 700 grams. Then in B, it asks you to calculate the density of the liquid. Density is mass divided by volume. Okay, the mass of the liquid, because we're trying to find the density of the liquid, is the 700 grams. And the volume of the liquid is given as 750 centimetres cubed. And when you plug that in, you get 0.93, and it's grams per centimetre cubed. Okay. Then the last bit of the question asks you to calculate the weight of the empty beaker. So we write the equation for weight. Weight is equal to mass multiplied by gravity. The mass of the empty beaker, it tells us, is 400 grams. But to work in the weight equation, that has to be converted into kilograms, the standard unit of mass, okay, which is 0.4 kilograms. So my mass is 0.4 and G is 10 because it's on Earth, and that gives us 4 newtons. Okay. Also, a bit of a clue that you're going to need to do more work so that you can spot this. It's worth 4 marks. So if you were just doing 400 times 10, that wouldn't be worth 4 marks. Okay, so just spot things like this. Okay, section 3 was the alternative to practical question. So we're measuring acceleration due to gravity by rolling a steel ball down a slope. It's 2 meters long. We've got graduations marked out, and it says, and lots of people miss this, draw the ball to show when it has travelled 60 centimetres. That was worth a mark. Okay, now the ball had this part of it touching 0, so the same part of the ball has to touch the 60, so that the whole thing has only moved 60. If you were to draw the ball like this, it would actually have travelled this far, which is further than 60. Okay. Then you had to find the average of the time taken. So you're just finding an average of those 3 numbers, but don't forget that it tells you to give your answer to 2 significant figures. Okay, so add them up, divide by 3, and then on your calculator you can then look at that and see that to 2 significant figures you get 0.87. And I'm going to take that number and I'm going to put it straight into the table, okay, because that was when it travelled 60 centimetres. Okay, so this is t. And then there was space for you to fill in some t squared values. Okay, so we're taking t, so doing 0.87, and we're squaring it. And that gives us 0.76. We're doing 0.99 squared, and it gives us 0.98. We're doing 1.1 squared, and that gives us 1.21, and that allows us to fill in the rest of our table. Okay, so you literally just square the numbers for t. Then you're asked to plot your graph. And it asks you to put d on the y-axis, t squared on the x, but they're very kind and they give you that. So you can see that each small square on your scale here is going to be equal to 0.02 going across each small square. Okay, and then between 60 to 80 is 20. So each square going up is worth 2. So you then plot your points. They need to be crosses, not dots. Okay, CIE are looking for that. And then you have to put the best fit line on. So what I do is I take my ruler and I twist it round so that I can look down onto it like this, so that I can see where the points are. And I twist it until I can see I've got a good line. Okay, so until it goes through as many points as possible. So you can see here, these ones perfectly lie on the line. And then I've got one just slightly above and one just slightly below. So that's really nice and balanced. And you draw that straight line through. If you draw sketchy lines like this, or thick lines like this, you don't get the mark. Okay.